Hola, buenos días. Thank you very much for Karina and Jose for inviting me for this school. This year I will start with geography. This year is very rich on the organization of various schools in cheminformatics. It shows the importance of our field. So the first school has been held in Strasbourg last summer. Now we have the first school for Latin America in Mexico City, and in few days I will attend another summer school another autumn school in Nara. Schools in Strasbourg and Nara, they are regular, and I firmly believe that your school in Mexico also will become regular. And hopefully one day I will be able to join you physically, not only with Zoom. Okay, anyway, coming back to my talk, to chemography. Just I would like to start, just chemography is a tool for big data analysis, and chemistry generates a lot of data. Some 10 to 9 compounds are physically available. A huge amount are huge virtual libraries, up to 10 to 26 compounds are available in pharmaceutical companies. And this last number is not too far from 10 to 33, estimated as the lowest bound of all drug-like molecules which could ever be synthesized. So we need new computational technology to analyze such a big data. One of solutions has been suggested by Tudor Aprera, who proposed to use the chemography approach in order to build special maps describing structure and properties of molecules. The question arises how such maps could be constructed. In cheminformatics, a molecule can be encoded by an ensemble of useful parameters calculated from chemical structure, from molecular graph, called by molecular descriptors. So in such a way, this ensemble of molecular descriptors form a vector which, like a fingerprint, characterizes the molecular structure. In such a way, a molecule could be considered as an object in n-dimensional chemical space defined by n molecular descriptors. Since we are not able to visualize an object in n-dimensional space, we need to reduce its dimensionality to 3 or to 2. Okay, there exist many mathematical methods of dimensionality reduction. Clearly, that the data distribution in two-dimensional space depends on the method used. This is illustrated on this slide, which shows application of 15 different methods of dimensionality reduction to the same data set of 100 actives, 100 inactives against acetylcholine esterase receptors. You see all images are different, but by some reasons we selected only one of them, which is called generative topographic mapping, or GTM. Few words about algorithm of GTM. This is briefly resumed on this slide. So let's suggest that we have a data cloud, and the first step, the algorithm inserts into data cloud a flexible sheet, which is called manifold. Then the data points are projected into the manifold, followed by the manifold unbanded. So in such a way, this data cloud in n-dimensional space, in our case, 3-dimensional space, is transformed into a dimensional space of the map, which is called latent space. Interesting particularity of GTM is that this algorithm allows not only to visualize the data in two-dimensional space, but also it generates the data probability distribution in both initial space of n descriptors and into the two-dimensional latent space. In the initial space, data probability distribution is modeled by ensemble of Gaussian functions localized at the node of rectangular grid superposed with the manifold. In the latent space, projection of a given molecule is described by the probability of its location in different nodes of a rectangular grid. And then this, what we can do, we can then transform ensemble of these probabilities, which are called responsibilities, to a vector which length is equal simply to the number of nodes of the grid. So this is some kind of descriptors which we, for a given molecule, which are based on this GTM mapping. So you see some sort of, let's say, like ink spot which is spread over the sheet of paper. But then we can add second molecule, third molecule, and in such a way accumulate these spots. And projection of many molecules gives us results in the such called density landscape, which shows the density distribution of the molecules in the chemical space. So we have this density landscape, which actually identifies the regions that are underpopulated or overpopulated. And then when we superimpose this map with the rectangular grid, we can also transfer the density values into vector. And in such a way, we can encode, means characterize the entire chemical library, whatever its size is, by one sole vector, which is called responsibility or density vector, whatever. Okay, and this map density, this density landscape is very convenient to analyze distribution of different chemotypes, as it is shown on this slide. So you have, for example, R1 area on the left, which accumulates thiophene, and or R3 area, which accommodates mostly heterocyclic amides. So, and the color code here characterizes the data density. So red areas correspond to highly populated areas in the chemical space. Now, I would like just to mention that generated topographic maps can also accommodate some information about various molecular properties, similar to the world map, which is with the help of the color code, may accommodate different kinds of information. For example, country frontiers, CO2 emission, population density, etc., etc. So, basically, there exist three types of GTM landscapes. So, density landscape, characterizing data density distribution, class landscape, characterizing population of activity classes, active, inactive, and activity or property landscape, which reports an average activity or property values in a given part of the map. So the meaning of the color code varies, depends on the type of the landscape. So in, let's say, on the left side, so you have a density landscape, red corresponds to dense areas. At the center, you have class landscape, which characterizes activity of compounds. So red zones are populated mostly by active compounds and blue inactives, whereas yellow and green contain both actives and inactives. So, and on the right, you have a property landscape. In this case, it shows a distribution of compounds according both to structure and a given property, which is here molecular weight. And here the red areas accommodate heavy molecules. Okay, so you can superpose again these maps with a grid and then calculate the class landscape value in the node of the grid. And in such a way, you can characterize the entire library by several vectors, characterizing either structure, chemical content of the library, chemical structures, or chemical structure and biological activity or physical chemical property. Okay. And so we published several papers showing that this activity and class landscape could be used in order to predict class, class label, active or inactive, or activity value using bias equation. So, and in such a way, activity landscape acts as a regression model, whereas class landscape as a classification model. And if, let's say, a compound is projected into the empty zone, it is considered as to be out of the model applicability domain. It means that the GTM maps, GTMs actually could identify its own applicability domain. So no data in the training, no training data in this area. Actually, the predictions could not be made. Okay, now a few words about molecular descriptors, because predictive performance of the model depends on molecular descriptors. We used such called easy fragment descriptors developed in the lab, and they represent subgraphs of molecular graph, so molecular fragments, which vary either by their topology. It could be atom and bond sequences or atom-centered fragments. So another kind of parameter for variation is size, and also we can vary atom labels. We can use as symbol of chemical elements or pharmacophores or force field atom types. And each subgraph is an individual descriptor, and count is descriptor value. And clearly that for a given set of molecules, we can generate several different pools of such descriptors, which could be tested as descriptors in machine learning models. And which descriptors are the best? So in fact, we generate many types of descriptors. We apply all of them, and then this is machine learning algorithm selects the best type of descriptors or several types, which leads to the most performant models. Okay. Now, since GTMs could be used for prediction, we can try to use them to profile chemical compounds with respect to different biological activities. And in this case, two scenarios could be considered. The first one suggests preparation of a series of single task models. It means that for each activity, we look for a particular, the best type of descriptors, and this type of descriptors is used to build a GTM. And another scenario corresponds to multitask modeling, in which we select one common type of descriptors, which allows us to build one sole map able to predict different activity classes. And we call this map, which predicts many different activities, we call this map universal. Actually, we managed to build such a universal map for the CHEML database, and this map delineates, let's say, a biologically relevant chemical space. So it is built roughly on 1.7 million compounds. It is built certainly on selected EZD descriptors, we tuned them, and it is able to predict more than 700 biological activities. So on this slide, you see on the left the density landscape, showing more dense or less dense areas. And on the right, several selected activity landscapes for different activities. And you may see that this activity landscape, the shape is different because simply we selected only those zones populated by compounds tested against this particular biological targets. Okay, now, but I spoke about this universal map. What is the meaning of this universality? So, we try to build a map able to accommodate variety of known chemotypes, to be able to distinguish different activity classes, to separate active and inactive within a given activity class, and what is very important, to be neighborhood behavior compliant, which means that molecules grouped together are expected to display similar activities, and are the same that similarity principle similar compounds possess similar activities must be respected. So we use this universal map to construct, to prepare a tool which we call ChemSpace Atlas, which is polyvalent tool, which accommodates more than 1 billion compounds and assembles more than 40,000 different maps and more than 1.5 million activity landscapes. And it has many options: data visualization, search, extraction of maximal common substructures, scaffold analysis, and it could be used for pharmacological profiling of new compounds with respect to more than 700 biological targets. And the information has been recently published in the SIM. Those who is interested to this tool, which is actually publicly available on our server, could look at this recent publication. Okay, now I would like to briefly discuss this application of this tool and some other tools developed in the lab to visual screening, analysis of large chemical collections, and in artificial intelligence-driven design of new molecules and reactions. So first concerning applications of GTM to virtual screening. So this is very straightforward. We have a chemical database of virtual or real compounds. We project this on the GTM activity or class landscape, and then we select the hits. So it works like any other machine learning model. So I would like to just to show one sole example. This study has been actually initiated at the very beginning of COVID pandemics, when any data, any biological tests against SARS-CoV-2 virus was not available. So we used data available for SARS-CoV-1. This virus has been more or less, let's say, well studied. So, and we built such called SARS-CoV relevant antiviral space for different genus, here alpha and beta for coughs, and particular interest represents beta genus, which corresponds to SARS and MERS viruses. So, as you may see, this map well separates these two genuses. So we use this map to screen more than 1 billion molecules from zinc database. So we selected a bit more than 500 hits. Then they were docked in the main protease binding site, main protease of SARS-CoV-2. And then we selected 10 hits, which were submitted to experiment. And finally, our collaborators from Moscow, from Chemoinformatics Center, which actually was able to work with viruses, they actually identified 2 confirmed macromolar M protease inhibitors, which are not toxic. So the next example concerns comparative analysis of large chemical libraries. And we will, in this presentation, I will consider 2 examples: an overlap between Campbell and zinc, and Campbell with a pool of DNA-encoded libraries. In the first study, we compared zinc database containing commercially available compounds with Campbell, collecting biologically relevant compounds, and altogether, more than 1 billion structures were considered. And the goal was to identify non-overlapping part of zinc containing chemotypes never tested biological tests, which could potentially enhance screening libraries. On the other hand, non-overlapping part of Campbell containing chemotypes missing in the commercial libraries could be recommended for the enhancement of biologically biased commercial libraries. Okay, and then started this project, we have discovered a typical problem of cartography of big data. A map resolution may not be sufficient to separate different compounds classes. So here on this map, so this map accommodates more than 3.5 million compounds from zinc and Campbell. So zinc areas populated exclusively by zinc are colored in red. Those exclusively populated by Campbell in black. But on this map, you don't see neither red nor black areas. You see only yellow or green, which populated by both. What does it mean? It means that the global manifold doesn't separate the classes. Actually, on the scheme on the right, you see that the compounds may form the clusters, red or black, but simply the manifold, global manifold, corresponds to the map of low resolution. It doesn't allow to separate the classes. What we can do, we can select particular areas, and for each area, we could create a separate map, which correspond to a series of maps of better resolution. And in such a way, we could try to separate the classes. So this technology has been applied to this particular case. So we select each zone. So for example, zone 1 here, which is green, which means it's a 50-50 Campbell and zinc. And then we prepare another map, this level 1 zoom. So we do this systematically. And then again, from the zone, green zone, we prepare another map. So we have 3 levels of hierarchically related maps. And then on the right map, which accommodates only for a bit more than 4,000 compounds, we identify both black zone of Campbell, populated exclusively by Campbell compounds, and brown and red zones exclusively populated by zinc compounds. So in such a way, we extracted the compounds from these zones, and then we made a maximal common substructure analysis. So we selected this maximal common substructures, or MCS, exclusively, which is unique for Campbell or unique for zinc. And so, in fact, the paper was entitled, as you may see on the bottom, "Searching for Hidden Treasures." And so, how many hidden treasures we have been identified? So we identified around 20,000 chemotypes missing in the commercial space, and more than 100,000 chemotypes never been biologically tested. And this information is actually available in supporting material and can be used actually for enrichment, either screening libraries or biologically biased commercial libraries. Okay, the next example concerns generation and analysis of general purposes DNA encoded libraries, or DEL. Each library represents a combinatorial collection of small molecules covalently attached to a short DNA tag. DNA technology now is very, let's say, widely used because it represents a valuable alternative to classical screening. Unlike parallel testing of compounds in separate wells in classical screening, the entire DEL is tested against a biological target in a single plot. So it is not possible to perform a cherry picking of DELs. So we are not able actually to take one compound from this cocktail, which is situated in one tube. So therefore, we must consider entire DEL as a one sole cheminformatic object. So A DEL results from 2 or 3 steps chemical reactions between selected building blocks. Using a collection of commercially available building blocks and selected reaction rules, one can generate thousands of DELs, each containing billions of molecules. The question arises, how to select for a given task an optimal DEL, for instance, DEL used in primary screening. We assumed that such a DEL is one the best covering the chemical space. We believe that it delineates a chemical space of biologically relevant molecules. Using a collection of 79,000 building blocks from eMolecules database, with the help of the eDesigner tool from Eli Lilly, we generated more than some 2.5 thousand DELs containing up to 1 billion molecules each. And then for each DEL, we randomly selected a set of 1 million compounds, and each sample was then intersected with the Camel database. In such a way, we have considered 2,500 class landscapes from which the best DELs were selected according to the coverage score. What is coverage score? So since we represent each DEL by one vector, we can actually identify Tanimoto coefficient, or so we can suggest several different metrics. So the paper resuming all these metrics actually will be submitted within 1 week. Okay, so then when we performed this operation, so we intersected each DEL with the Campbell, so we then performed the ranking, and with our great surprise, the best DEL overlapped with Campbell more than by 50%. So then we identified the DELs which the best cover remaining space, and 3 DELs already cover more than 80%, and 5 DELs more than let's say then 85%. And what is interesting that all DELs they don't cover entire Campbell chemical space. You may see on the last map on the right some gray area corresponding just to Campbell, which is occupied by natural products and their analogs, which certainly are not present in DNA encoded libraries. Yes. What's also interesting, so traditionally people used to compare the database. They used a histogram showing the distribution of some physical chemical properties, for example, octanol water distribution coefficient. So you have 3 distributions, one on the top of Campbell, and then for 2 DELs. And you may see that they are similar. They have a peak at roughly at 4 log p equal to 4. And you can, let's say, draw a conclusion that DEL1 is similar to DEL2 with respect to at least log p. But then when you look at the maps, you may see that the data distribution in chemical space is completely different in DEL1 and DEL2. So you may ask if, let's say, these histograms give you relevant information. Yeah, the last part of my talk corresponds to application of cartography in combination with an artificial intelligence tools in order to generate new molecules of reactions. So I would like just to start with this slide, which is not chemical enough. So this is a painting which has been sold for more than $400,000 on Christie's, and the signature is this is made fully by artificial intelligence, and the signature indicates the basic formulas of generated adversarial networks, the GANs, which actually the method which was used by artificial intelligence. How actually AI proceeded? Actually, the algorithm analyzed more than 15,000 paintings, and then the trained model allowed to generate a new masterpiece. And this is actually, this principle can be used in chemistry when the artificial intelligence tool looks at the content of chemical database, of reaction database, or molecular database, and this knowledge allows it to generate either new molecules or new transformation. So, and then now how molecular cartography can be used in this for this purpose. So just one of the simplest way to generate molecules is application of deep learning architecture, which is called the autoencoder. Autoencoder, the goal is to reproduce the object itself. So in this case, in chemistry, we try to reproduce the text string, smiles, which encodes chemical structure. So as input, you have smiles, then the neural network creates its numerical image as a vector on such called latent variables, and then it outputs again the same smiles. So you have text, which is transformed in real numbers, and then to text. So, and then this vector of latent variables could actually be used as a descriptors, and then we can, in fact, as soon as this network, deep neural network is trained, so we can actually select a data point in this space of latent vectors, and a little bit shake this vector, and to send it to the decoder, which generates new smiles string, which is then transformed in the chemical structure. So the question arises how to select a good seed vector from which we can generate valid structures possessing particular activity. Yes, so again, this example, you know, so we have here the labels, actives and inactives, and we consider seed1, which is active, but surrounded by inactives, and seed2, active surrounded by actives, and we can conclude that seed2 is more beneficial, but in order to identify it, we can use dimensionality reduction or GTMs, and then to sample, to select a seed in the center of area of the cluster on GTM populated by active molecules. So I wouldn't like to give you the technical details. They are on the slide in our publication, but then so we just demonstrated that how it does work. So we, for A2A receptor, we trained the autoencoder on the chemo data set, and then we built activity landscape for A2A receptor. We selected a zone populated exclusively by actives, and then we sampled from the zones, and in such a way we generated new compounds which were enriched with new scaffolds. So this is the way. And then very briefly another example which is related to a generation of chemical transformation. So you know, so we actually we intended to, let's say, repeat exercise for which Akira Suzuki obtained his Nobel Prize in 2010. This is the Suzuki-Kaplan reaction. And so we expected that artificial intelligence helped us to discover new type of chemical reaction, and then we may pretend for Nobel Prize. Unfortunately, it was not the case. Anyway, so but just to say that chemical reactions is a difficult object because they involved in many molecular graphs, and they are unbalanced, and then actually a priori it's difficult to detect novel type of transformation. So we solved all these problems. So we encoded chemical reactions and by a single graph, which we called condensed graph of reaction. And finally, we generated new, let's say, variants, still unseen variants of Suzuki-like reactions. And then afterwards, we found 5 out of 13 in SciFinder, which contained much more reactions. And these reactions were not in the training set, certainly. which shows that artificial intelligence could be used potentially to generate new chemical transformations. So I approach to the end. So, well, yeah, so this slide shows that, the chemistry, so which transformations were, let's say, designed by AI. They correspond either to exotic coupling or exotic living groups. So chemists, synthetic chemists present here could, let's say, easily see this. Anyway, it was published in scientific reports. You can actually look at the details there. So just to finalize, I try to convince you that chemography is a very interesting and efficient analysis of chemical space. And I would like just to thank my group members in Strasbourg and my collaborators within 2 European projects, my colleagues from Kyiv participated in Hidden Treasures project and the Chemoinformatics Center in Moscow, who measured anti-CoV-2 activity, and various industrial partners. And I would like to thank all of you for your kind attention.